Welcome to 2.4, ladies and gentlemen, and I've entitled it Your First Physics Equation. I called it Your First Physics Equation because you're literally probably going to get 30 to 40 physics equations over the entire semester and year, and this is the very first one. It deals with velocity, and I'm just going to come right out and give it to you here. It is velocity equals distance over time. That's it. V equals d over t. V stands for velocity. D is displacement. Sometimes I flippantly call it distance, but really it's displacement, because if your displacement is negative, that means your velocity is negative, and time is a scalar. There's no positives or negatives to it. So, but there is a difference. Now, this is what we call the average velocity. There's a difference between average velocity and instantaneous velocity. Average velocity is you take an entire distance and time, you take an entire time and you figure out the distance for that. So for instance, let's say you're taking a trip to Dubuque. So you get in your car and you drive, you stop and get gas, and then you maybe drive and pick your friends up. And then you go through some stoplights to get out of Platteville, and then you take the on-ramp, and you're doing 65, you do an exit ramp. Your velocity is changing throughout that entire process, meaning when you stop to get gas, your velocity is 0. That's your instantaneous velocity. When you accelerate up to go pick up your friends, maybe you're doing 35 across the street. That's an instantaneous velocity. As you slow down, your velocity is instantly different amounts as it gets slower and slower and slower, or faster and faster and faster. Your average velocity, let's say Dubuque is 10 miles away, and it took you maybe an hour to get there. So your average velocity is 10 miles per hour. It doesn't factor in, your average is your total displacement divided by your total time. The instantaneous velocity is the velocity at any given time instant. Another way to do it is, it's actually, some people call it, it's the slope of the position versus time graph at at any point. Not only is it the slope of the position versus time graph, it's the slope of the tangent of the position versus time graph at any point. And let me give you an example here. Like, let's say I had a very simple position versus time graph. A displacement versus time graph, and let's say it did this. So here I'm moving at a constant velocity, and then here I'm standing still. But what if my position versus time graph, so the speed at any point along here is the same, and the slope at all those lines is exactly the same. But what if my position versus time graph was a little bit more complicated? What if it did something like this, where I'm getting faster and faster and faster? My speed right here is a lot different than my speed right here, which is even more different than my speed right there. Here's that tangent line. The slope of this tangent is equal to the instantaneous velocity. Same right here. This one, the slope of the tangent looks something like that. And then I've got this point right here. Maybe the tangent's like this. And you can see that I'm getting faster. The slope is increasing, so I'm getting faster as time goes by. So that's the difference between instantaneous velocity and average velocity. Let me give you another example. I've got here a position versus time graph. And what I'm just going to make up a general like this. So I could say to you, what's my average velocity for the first 5 seconds. First 2 seconds. That's my total distance, displacement over my time. So in the first 2 seconds, I really don't go anywhere. So it's 0. What if I change that to, say, the first 6 seconds? So my total distance, I start right here at 0, and I end over here at -1. So my displacement now is -1 meters, and the time it takes me is 6 seconds. So you do 1 divided by 6, and that comes out to be -0.17. 16 repeating, but it's 17. What if I switched this and I said, what's my average velocity for the 2 to 6 seconds? That's a little bit different. So here, I'm going from here to here, so my displacement is still -1 meters, but now it's only taking place over 4 seconds, so that's -0.25. That's actually my speed. My instantaneous speed at 4 seconds is -0.25 meters per second. And that's what my speed is right here. That's also my speed right there. But my average speed over the entire interval 0 to 6 seconds is equal to -0.17 meters per second. There's kind of that's the gist of the difference between instantaneous velocity and average velocity. Let me give you another example problem where you're going to see something like this. It says, Mr. Hare runs at a speed of 8.3 meters per second. I figured I run a 100-meter dash in like 12 seconds, so that's what was my guess. And I looked up Usain Bolt. He runs at 27.44 miles an hour, which means he runs at 12.3 meters per second, which is like literally almost twice as fast as me. It's like 50% faster than me. If I had a 55-meter head start, how long would it take Mr. Bolt to catch me? And then B, where would Usain Bolt catch me? Now, before I get into this, I've got just a fun little graphic I found online that showed the relative speeds of certain animals. And you can see Usain Bolt, he's faster than an elephant, a little faster, slower than a domestic cat. Here we got a cheetah up there going like 70 miles an hour, which is crazy. But I wanted to show you this other video right here. It's at a NFL football combine. These talking heads, they talk football all the time. So one of them, they put him out at a combine and had him run a 40-yard dash, and they compared him to all these different football players, and it's just absolutely hilarious to see truly how fast some of these athletes really are.
All right, Cam's time. This is when it's always fun, right?
Yeah.
Why don't we start out with perhaps the number 1 pick in the draft, Jameis Winston, the quarterback for Florida State, the Heisman Trophy winner. Jameis ran 4.97, Rich. All right. Okay.
Yeah.
Okay. Well, what about the number 2 quarterback, or maybe the number 1 quarterback, Marcus Mariota, who ran the fastest time as a quarterback? And we gave you a little bit of a head start there.
Marcus ran 4.52, Rich. Don't feel bad. Okay. You get a 10-yard head start on this one. Kevin White from West Virginia, the wide receiver. 10-yard for you, Rich. No shot. And here comes Kevin.
So he gets a 10-yard head start on a 40-yard dash. So like he literally was he was a quarter of the way there and still got beat.
Rich.
For Kevin White?
15.
15
Philip
yards?
Dorsett from the University of Miami, the wide receiver. You're getting 15. Run, Rich.
No, they didn't give him
Stand up
real
and run.
That's like they're standing still.
So that's a bit of a problem for you there. Okay. Well, how about the UAB Blazer, J.J. Nelson?
Who weighs about 105 pounds. And, Rich, they said they gave you 15 yards on this.
And J.J. Nelson ran 4.28.
Okay, let's go to the big boys. You know you like to run.
Now this is where it gets really funny. They start putting him up against these 300-pound linemen.
Leonard Williams.
And let's see how we did with Leonard Williams.
Oh, man.
Leonard Williams, 302 pounds.
Hey, Rich has kids, man. They're watching
Okay.
this.
You want them big?
Give me
You want
Danny
them big?
Shelton.
Let's
I
go
want
big.
Danny Shelton.
Okay, you want Danny Shelton? You're getting Danny
Susie, turn the kid's head.
Please get in the shot with him. Stay in the shot.
5.64.
Okay, Charles.
Mike Mack, it's been your week to talk
Okay, that's enough. Let's go back to the question. Now, this question, at first, it seems kind of tricky. There's a few ways to do this problem. One way is to just brute force it the caveman way, where you make like a table and you're like, okay. So you've got Usain and Hare. So at time equals 0, Usain is at, let's call him at negative 55 and Mr. Hare is at 0. And then at 1 second later, Mr. Hare is 8.3 meters farther and Usain is 12. So you take 55 minus 12.3. So that's going to be negative 40. Is that 48? 47.7? I think so. So you could just keep going down. This is what's called the recursive formula. If you remember back from algebra, you have to find the thing before it, and again, I would be at 16.6 and I subtract another 12 off of him. So like 33 point whatever 4. But this would take you all day. And maybe you wouldn't even find maybe they don't meet exactly at 1 second. So that's going to be even more complicated if they meet at like an in between. The better way that I think is to make a position versus time graph. So displacement in meters versus time in seconds. So here's what this looks like. Mr. Hare, we're going to say he starts at 0 and he runs like this. And Usain starts down here at 55 meters later and he runs a lot faster. And my real question is, where do these things meet? Right? So I'll do this. Here's at negative 55. This is 0. And check this out. I'm going to make a mathematical model that represents Usain Bolt. I'm going to say that y equals 12.3 x minus 55. Because Usain runs at 12.3 meters every second. So every second that ticks by, he goes 12.3 meters farther. Another second, 12. That's actually the slope. Remember, this is the slope of our line. And then Mr. Hare, his is easy to model. I run at 8.3 meters per second, and my y-intercept is 0. So the real question is, when do these two things equal each other? So you can very simply say, where does 8.3x equal 12.3x minus 55? So you solve this. So you take 8.3 minus 12.3, and that's going to be negative 4. So I divide by negative 4. So I take 55 negative 55 divided by negative 4, and I get 13.75. So that's the x value. Where they meet, 13.75. And the x value is time. So how long will it take Mr. Bolt to catch Mr. Hare? It will take I can use two significant figures. 14 seconds for part A. Where will he catch me? You see how quickly I did that? Like, I would still be doing that recursive formula of figuring out, and again, it's in the between. So you would have to do this 14 times to get here. To figure out where, then I just plug this back in. I'm going to plug it into here because that's the easiest one. So I'm going to take 13.75 times 8.3. Now notice what I did. I didn't take 14 times 8.3. I took my original number. I'm going to multiply it by 8.3, and then I'm going to round it. I'm going to round it to 110. So just put exact numbers in when you're doing your equations and round at the very end. When we start doing these equations, that's a common question I get with a lot of people. Where do I round it? Round it at the very end. So where does he catch me? At 110 meters. So pretty much, no joke. if I had a 55-meter head start, he's going to catch me. Like, he runs almost – if this was a 100-yard dash, he would almost catch me if I had a fully one-half track head start. If I started 50 meters ahead of him, golly, I bet he would catch me right at the end. So what a crazy race that would look like to see somebody at a 100-yard dash. They start at the 50-meter mark, and then they get caught at the end by someone who's twice as far away as them. Just goes to show you how crazy fast he really is.